Hey, Spencer here, going over video presentation number 2. So let's jump right into it. Let's set this up. Perfect. Alright, so for our given problem, we are asked to show that there's no flow through the wall. We got to determine the velocity distribution along the wall and determine the pressure distribution along the wall. So we are given our velocity potential function as phi here, and we're going to use that to determine cases or problems A, B, and C. So jump right in this. In order to show that there's no flow through the wall, we're going to take the partial derivative, or we're going to basically figure out the velocity in the x direction at the wall. And the wall is at this point right here. So to do so, we got to take the partial derivative with respect to x of this phi function, or the velocity potential function. So to do so, we're going to label this part A. Move this light over a little bit. It might make it look a little bit better. All right, so part A, we're going to say that we need to find the velocity in the x direction, which is equal to u in this case. So in order to do so, we're going to say u equals e phi over with respect to x. And in this case, our phi function is this big old thing right here. So we're going to substitute out partial x of m over 4 pi ln of x minus l squared plus y squared plus ln of x plus l squared, plus y squared. Alright, and so we're going to take the derivative with respect to x here in order to get our x component of the velocity. So doing that, this goes out to the front because it's a constant. We're going to take that term as a constant, so we're going to get u is equals to m over 4 pi, and then the inner piece of this, we're going to take the derivative of both of these sets right here with respect to x. So if you do so, you get 2 times x minus l, 2 times x minus l over x minus l squared plus y squared. That's for this first term right here. And for the second one right here, it's going to give us pretty much the same thing, except place it with that plus sign. 2 times x plus l over x plus l squared plus y squared. Alrighty, and here we're going to substitute in our x position because we're trying to show that there's no velocity at the wall. So at the wall, this x position right there is going to equal to 0. So we're going to say x equals 0. We'll substitute. So x equals 0 at the wall. So we're going to go ahead and substitute that in. U equals m over 4 pi times 2 times 0 minus l over x minus l squared plus y squared plus 2 over x plus l. Oh, wait. Forgot to substitute these zeros in. 0 minus l squared, 0 plus l over 0 plus l squared plus y squared. When you do so, these two terms cancel out because you get u equals m over 4 pi times negative 2L over L squared plus Y squared plus 2L over L squared plus Y squared. So we can see that these two cancel out each other to 0. And 0 times this m over 4 pi term is going to give us 0. So this shows that our velocity at the wall is going to equal to 0, which means that we have a stagnation point right there at the wall, meaning that there is no flow through the wall. So from that we can determine that there is no flow through the wall. Alright, cool. That is our part A. Moving on to part B, we're going to do very similar steps here, except we're just going to take the derivative with respect to y in this term, because we have to determine the velocity distribution along the wall. So along the wall, we could say that that is our y direction up and down the wall. So we're going to go ahead and find the velocity in the y direction. That is equal to v in our case. So v is going to be equal to the partial of phi over partial y, which in this case is just derivative with respect to y of our big main function again, m over 4 pi ln natural log of x minus L squared plus y squared plus log of x plus L squared plus y squared. Alright, perfect. Alright, so doing so, we're going to get that v is equals to m over 4 pi. Again, we're taking that constant out. Then we're just going to take the derivative of these two terms right here with respect to y. So taking it with term 1 is going to give us 2y over x minus L squared plus y squared plus another 2y over x minus L squared plus y squared. And these derivatives could be done simply through a couple chain rule steps. And when you take things in respect to y or respect to x, these, in this case, when we take it with respect to y, this term right here is a constant. Taking the derivative of it just goes to 0, so that's why we get the 2y on top. And then on the bottom, we get it over this bottom function because of this whole natural log thing. When you take the derivative of natural log, it goes to 1 over the function. So that's where this comes from. If you're confused on that, simple Symbolab, anything like that can show more detailed steps, but it's a pretty simple derivative in our case here. So anyways, from there, we want to substitute in very similarly to step 1, substitute, disregard my spelling. Anyway, substitute x equals to 0 here because, again, we're taking it at this x position at the wall, which in our case is going to be 0. And when x is equal to 0, we can say that the velocity is equal to the velocity distribution at the wall, which we're going to call VW here. So, there we go. All right. So we're going to substitute those in. We get VW, velocity distribution at the wall, is equals to m over 4 pi times 2y over 0 minus L squared plus y squared plus 2y over 0 plus L squared plus y squared. When you do this, it cancels out. VW is equals to 4 m over 4 pi of 2y plus 2y over L squared plus y squared. This 4 is going to cancel here with the 2 plus 2. And that's going to leave us with our velocity distribution at the wall being equal to m over pi times y over L squared plus y squared. Perfect. All right. Now that we have those two steps done, shine a little more light over here. Might make it a little bit easier to see. Perfect. All right. Now that we have those two steps done, we're going to move on to the third and final step of the problem. In this case, it's asking for the pressure distribution along the wall, assuming that P is equal to P naught, far from the source. So to do so, we're just going to use Bernoulli's here. Just a quick, easy Bernoulli's problem. Label this part C. Alright, so doing so, we're going to use our typical equation of P1 plus 1/2 rho V1 squared plus rho G Z1 is equals to P2 plus 1/2 rho V2 squared plus rho G Z2. So in our given case, we can acknowledge that Z1 is equal to Z2 because they are both in the same position here. Both can be taken at that same position. So Z1 is equal to Z2, therefore we can cancel these out. Boom. P1 is equal to P naught, like the problem said. Here it says P is equal to P naught. This is just our P1 value. So P1 is equal to P naught. V2 is equal to the velocity distribution at the wall here, right there. V1 is going to be equal to 0 because V1 is going to be equal to our initial velocity at the source. And at the source here, our initial velocity is going to be equal to 0 because the source is not moving. And P2 is going to be equal to the pressure at the wall. Alrighty, substituting those things in is going to give us, we can cancel this out, this term out, going to go to 0, cancel the z's out, so that's going to leave us with P naught, which is our P1 term over here, is equal to pressure at the wall plus 1/2 rho velocity distribution at the wall squared. From there, we can just switch this around real quick and subtract this term over here to the other side to get the P wall on one side. So the pressure at the wall is going to equal the pressure naught minus 1/2 rho velocity at the wall squared. And here we're going to substitute in our velocity at the wall, which we found in our previous step right here. We're going to substitute this in into the Bernoulli's equation. And that's going to give us P wall equals to P naught minus 1/2 rho times m over pi times y over L squared plus y squared. From that last final step, just simplify down. We're going to get that our pressure at the wall is equal to P, pressure naught minus 1/2 rho, sorry, that's a rho there, m squared over pi squared times y squared over l squared plus y squared squared. Sorry, there's a lot of squares there. And that is our final answer for step C. Perfect. Go ahead and sign this thing real quick. Sorry, that is a terrible signature, but it's okay. And that is going to do it for our video presentation number 2. Thank you.